Hi, my name is Chase Janetta, and I am part of Team AMORE. We're located in Sault Ste. Marie, Michigan, as part of Lake Superior State University. Team AMORE consists primarily of undergraduate students. We compete in events such as RoboBoat, Robotics, and VRX. This is actually the first competition where we're bringing our main vessel, the WAMV. So the WAMV is a 16 by 8 foot catamaran-style vessel. We use 4 thrusters, 2 Newport NT300s, and 2 Minn Kota PowerDrive V2s, all off-the-shelf thrusters that you'd see on your standard fishing boat. For the Robotics challenge, we plan to integrate a drone onto the WAMV for an autonomous launch and recovery process. So doing that, we had to design a landing platform and then integrate the Unmanned Aerial Vehicle with the WAMV. For the drone, we chose to use the Holybro X500 V2. It's just a standard off-the-shelf drone you can buy. But what we did is we fitted it with a Jetson Nano that we used to communicate back and forth with the WAMV. So at all times, we have communication set up that we can see where the drone is, and we can also see where the WAMV is, and then have them communicate during autonomy. But we did not have a landing and recovery sequence program. Using MATLAB, we designed the controllers required to actually launch and recover the drone from the WAMV autonomously. So to start off the MATLAB simulation for the launch and recovery process, we first started off with the dynamic model for the drone. So basically what that does is it models disturbances and forces, Coriolis and centrifugal force vector, gravitational force and torque vector. Basically just have the drone fly up for a set amount of time, in this case being about 10 seconds. Using the dynamic model for the drone, we developed a proportional controller. Proportional controller literally just means the response to any errors seen in the drone, the response is proportional to that. So, using a little bit of math and a little bit of PID controller theory, we are able to generate a plot that you will see here, where you can see the response of the drone over time. The next step in developing this controller is developing the derivative portion of the PID controller. We have the proportional and derivative controller, where for 15 seconds the drone will just basically move to a point that we give it. And then here we have the actual output. We got it to go to a point, but we want to integrate another term so that it can get to that point a little bit more smooth. In doing that, we integrate the I term. So now we have a PID controller, proportional, integral, and derivative. That controller should give us a little bit more control over how the UAV responds to disturbances such as wind, pretty much anything that it would see when it would be out flying this mission. Propeller velocity over time, forces in each direction over time, as well as the position over time. With the working PID controller for the UAV, we now integrate the USV. The USV follows the same trajectory of the UAV, above it at about an altitude of 10 meters for about 60 seconds, and then finally the UAV initiates its landing sequence. Running the simulation right here, got some nice outputs of starboard and port thrust. Since it is differential thrust, we can see that they both have different thrust outputs. And here is the finalized project. We have the UAV take off, navigate to a waypoint, and it then follows the trajectory of the USV and then eventually lands. So in doing this MATLAB simulation, we were able to verify that we could land the drone on the USV and successfully recover it. In verifying this controller, I learned a lot about MATLAB. I was very surprised with just the amount of capabilities using MATLAB and the software, just how much you can actually do with it. We look forward to using this for our drone and our WAMV at Robotics in 2024.